Okay, last week we covered P graph, P chart and C chart. So this will be the illustration of what is P chart and C chart. All right. So what's the differences between P chart and C chart is the axis. So when you plot P chart, you need proportional defective. Proportional defective. So again, as I mentioned just now, there's some changes to your final exam. So take note. Take note on that. Those just come in, one ask what your friend what I'm saying just now. Okay. So you have two equation with this ULC, CLC. So you need to find the three lines with this mean at the center, ULC above, ULC below. Then there's the equation to calculate the standard variation, which is the square root of average bracket 1 minus average divided by total of sample. Okay. So also we go through this example one in the previous lecture, right? So what is differences between P chart and C chart? P chart, you look at how many things or how many prototypes that you collect at the end of the your research or at the end of your survey. So remember the n here is 2000, 100 divided by 20. And then how to get the number of defective is that because every sampling you take 100 sample, 100 100 genes in this case. So read carefully when it comes to your final exam. It will tell you each time the inspector take how many sample or how many engines, how many sugars, how many break from the sample. So that is the n that you need to take. Like for example, 6 divided by 100, you get 0.06. Your final exam won't be 100, it will be another odd number. Okay, so once you get the wrong number, the whole question is wrong. So make sure you study hard for your P chart. Okay. Okay, so the rest already get the numbers, and this is the expected answer for the tutorial question number 1, which is in this case, after you plot the graph or plot the chart, the next question you'll be coming, you will be seeing is you need to answer whether what happened to this chart. You need to know how to interpret the chart. All right. So either it's in control or out of control. In this case, there are 2 points that is out of control, but most of the data still within the ULC and CLC. However, there's a uptrend of this one. Right? The trend is going up towards ULC. So some corrective action need to tune back. It means the machine need to tune back to the mean value. Okay. Okay. So again, one thing you need to be careful is the percentage of the question. So it is how many sigma that you're using. So like for example, this example, it tells you that you have approximate 99% of variability of the production process. 99% is cover 3 sigma to the left and to the right. Okay, your sigma graph, you have a positive and negative side. So you have 99% means cover left hand side and right hand side. Okay, 3 sigma, 3 sigma. So your Z is 3. So read carefully whether it's 99 or other numbers. Okay. As you read, it's a upward or downward trend, right? Go upward trend or in control. Okay. C chart, the y-axis, it will be the number of defect rather than proportional defective. So this is a C chart, number of defect. Okay, so same, you need to calculate the mean number, the ULC and CLC. But the notation we use for C chart is C hat rather than P hat. Okay, so the application of this using C chart will be the number of defect in the pen job, okay, and the standard variation is you take the square root of your mean, your different equation for the C chart. If those coming late one, ask your friend what I say to the class just now. There's some changes to your final exam question. So for the second example, you use the calculation and then you plot the graph. So you get the mean, you get the ULC, CLC, and then you need to answer the same question. What happened to this process? Is this process in control or out of control? In this case, all the data is within ULC and CLC. And again, this data is 3 sigma or 99% of the variable data. Okay, so as you narrow down the percentage, narrow down the sigma, 2 sigma, 1 sigma, then your process will be more and more strict. Means if you have 1 sigma, it will be around here. So some point will be out of this one. So you need to, when you tell your customers or when you tell the production line or QA department, you need to be sure, are you speaking in the same dimension or not? If the department is measuring in 3 sigma, but your customer, your contract is maybe 2 sigma, then you need to tell the quality department. If not, then the reject rate. Your means in internal is you pass the QA system. However, when it send to the customer side, when they measure, it's out of the spec. So the whole lot will reject back. Lot here means one shipment. One shipment maybe it cover 1 million piece. So when you reject, you need to cover the return shipment. The customer won't bear any return shipment. Okay, so there are some losses there. Okay. Okay, so this one you read lah. So another one is the R chart and mean chart. So previously, we studied about P chart and C chart. So when we have a continuous variable, for example, you measure weight or volume, then we will use R chart and bar chart, right? Or mean chart. So there are two. Range chart is for dispersion of sample. Mean chart is for average, process average. Again, these two chart, R chart and mean chart, is for continuous variable. Okay, so the previous P chart, C chart, you take sample, then you stop, and you study what is the process. This one is continuous one. Okay, the rest you read. So mean chart is sample, blah, blah, blah. Okay. When did you use the mean chart? Usually the sample size is very, very small, less than 10 piece one time. Right? Okay, so the rest you read. There are two cases lah. Two cases. So, but in this case, I won't ask you. So if you use mean chart and your standard variation is known, then formula you use standard variation use, but standard variation is unknown, then you use a table based on the sample range. So there is a table if you are using mean chart. So let's look at the form of the equation is almost the same. ULC is average plus the standard variation. Z is the sigma, the control value, sigma. Then this is a standard variation. It's a similar pattern like P chart and C chart. It's just that in this case, because you are looking at mean chart, so you are looking at the mean value, then you take the mean of the mean. You take average of all the mean value. Okay. However, the calculation for standard variation is a bit different. You take sigma, standard variation, divided by square root of your numbers. Okay, there is a different equation for mean chart. For mean chart. Okay. So let's say you're having these cases. So you are in a tooling company and you're producing a strip ring bearings, and bearings means like the the bearing. So it look like a donut, and so I tell you how they do the sampling. They measure the outside diameter, and the employee take 10 sample during the 10 days period for 5 strip ring bearing. Okay, so every day they take 5, take 10 times, but each time they take 5 bearings. Okay, and measure diameter of the bearing. So you see the table here. So you have a subgroup 1, 2, 3, 4, 5 until 10, means it take 10 times. And this is the observation. So each time you measure 1, 2, 3, 4, 5. So once you see the table, you know actually what question asks you already, right? For the previous, it gives you defect, number of defect. But here you see the measurement. So measurements, one is either mean or R chart. There are 2 types of chart. When you see there's a continuous measurements, you measure 1 time, 2 times, 3 times, 4 times. Okay, you'll see this one. Huh? No. I only ask you 2 types of chart. Okay. Yeah. Right. Those come late one, I already give you some hints. There are some changes to your final exam question. Okay, so so in this case, you'll get your mean. For example, you take this, 1, 2, 3, 4, 5 value divided by 5, you get 4.98. Then you do the rest, you'll get the average. Okay. Then they tell you from the past historical data, process standard variation is 0.08. They tell you the standard variation already, 0.08. The company wants to develop a control chart of 3 sigma limit to monitor the process in the future. So you take the average of average. So you take the average of average, you add all the average value, you get 50.09. Divided by 10 times you take sample. So you get 5 point something. Then control limit, still the same. You take average plus Z, the sigma value, plus the standard variation. In this case, it tells you directly the the okay, so this one, the standard variation is a sample like sigma. Sigma is a standard variation. So the one that you use for mean chart is standard variation of sample means. So the question does now give you the standard variation. So you need to calculate the standard variation of sample means by using standard variation divided by square root of your number of sample. So in this case, although the question gives you standard variation, to plot mean chart, you cannot directly use this value. Okay, you need to use the equation, okay, divided by square root of number of time you take. Okay, then you get one value. Then you do the same for L, lower control limit, but the negative value. Okay, so you get 2 line, and then you get the mean, you get 3 line. Important in control chart, you have a 3 line, like you playing badminton. Where's your in and out? Okay, once that, in this case, early observation, once you have the ULC, lower upper control limit and lower and upper control limit, you have 5 point something, 4 points, about 5. So you look at the average there, is almost everything there, but maybe it's very difficult to see. What you do is you plot the chart. Okay. So once you plot the chart, you will see all the value here is within the process control. Okay. Okay. So just now is standard variation is known. What if the standard variation is unknown? So if the question tell you standard variation is unknown, then you use another equation where you need to use a standard table for this calculation. Okay. So you change equation a little bit. there are two unknown, A2 and R. Okay, A2 and R, you no longer use the Z value because your standard variation is unknown. Means the Z you don't know. So when you don't know, but in this case, you're referring to a standard table developed by statistics people. Already have a standard chart for that. So this question, when you see the question mentioned standard variation is unknown, straight away you refer to table to find the value. So ULC and CLC, it give you this. You are referring to table. What you're looking for is A value and R value in the table. This one you can calculate from the table, from the question, right? So let's say you have, this is the chart. If this kind of question come out lah, okay. So you'll see N sample, A value, D value, and so on. So you have D3 and D4. So in this case, just now the equation here, you're seeing A, right? So just now you're seeing a range chart and mean chart. For mean chart, you are using A value in this one. You're using this column. But later you'll see another chart is called range chart. You're using D3 and D4. Even on the table, you tell you factor for mean chart, factor for R chart. Okay. So in this case, we are referring to these two columns at this moment. Okay. So if you look at the same example like just now, the bearing company. So the same table, they want to develop the mean chart to monitor the process, but in this case, they don't tell you the standard variation. Okay. The R value is given here. Add one more column compared to the previous one. Okay. So how do you do? So you calculate the R bar, okay, by determining the range of each sample, computing difference between the highest and lowest value in our. So how you do? So you calculate the R value, R hat value. So you take the sum of R value divided by K. In this case, you sum up all the R. Then you get 1.15 divided by 10 sample. You get the R bar. Then you pull out this equation. In this case, because you are plotting, the standard variation is unknown, so you're using this equation, x double hat means average or average plus A2 R bar. Okay. So, okay. So you have the R hat and X double hat, 5 cm in this case. So once you have this one, you refer to the table. So since you are having this 1, 2, 3, 4, 5 measurement each time, like first time you measure 5.02, second measurement 5.01, 4 point something. So 1, 2, 3, 4, 5. So when you refer to the table, what you do, you take number of sample n here, 5. Then you take for factor of mean 5, you straight away read the number 0.58 from the table. Okay. Okay. So you put the numbers, you plug into the equation. Okay. Plug into the equation. You get one number. You plug to another ULC equation. You will get the numbers. Okay. So every time control chart, you need 3 numbers: average, ULC, LCL. Okay. What is so special about this mean chart is that when you don't know the standard variation or the question asks you, they want you to use they don't have the standard variation for the sample, then you refer to the table by using the A value from the table. Okay. So in this case, when you plot the graph, you will see the value, the process is in control, out of control. In control, however, when you are measuring sample 4 until sample 9, there is an uptrend towards ULC, but it dropped back again. Okay, so this is a mean, again, mean chart is a small, very small sample. So what you do is you continue. If you're not confident about this chart, what you do, you do run one more time the process by collecting the same 10 samples. Then you compare the two graphs, whether you see the similar trend or not. Means maybe when you come to station 4, there is a error already. But however, when it comes to station 9, somehow the dimension return back. Maybe there is a compression station, because maybe at station 4 you do cutting. So when you cut, when the machine you cut, maybe the cutter, the blade is not sharp enough. So the dimension is keep becoming bigger and bigger. But however, when it comes to compression, when you assembly things, there is a compression machine. You want to hit the things and join together. So when you reach that station, suddenly everything fit into the specification. It bounced back to, when it comes to station number 10, it suddenly bounced back. Yes, it's still under control. Oh. Yes, but you need to monitor. In this case, I will ask the QA process to run one more test, so that we'll see whether the similar pattern come out or not. If the similar pattern come out, then I need to monitor what happened to station 4 and station 9. Yeah, or even station 10. Like what actually make the sample bounce back to the mean. Okay. Sometimes it's because of the operator, they are talking to each other, then maybe the time that they press the button is different. So maybe it makes some different there. Okay. Right. Another type of chart is called R chart or range chart. So this one is range is different between the smallest and largest value. So in this case, you straight away use from the table. URC, you use D4 from a table. Lower control limit, you use D3 from the table. Okay, the rest question you see on the screen here. Okay, so the same table that you see, but now you use the same table from the bearing company, the R value just now, but now you want to use the R chart for the control chart. So in this case, you use D3 and D4 for the R value. Okay. So in this case, your R value, D3 and D4, D3 is 0, D4 is 2 point something. So you plug into this equation. So your LCL is 0, because the D3 value from a table is 0. 0 multiplied by anything becomes 0. But the ULC is double of your average, 2 point something. So when you plug in the number and you plot the graph, you get all this number, and then you plot the graph. So you'll see the graph will become smaller and smaller, the range. Right? The range will become smaller and smaller. And in this case, you see actually the value is fluctuating between 0.6 and 0.8. So when you use the range tools or range chart to monitor the process, actually the process is in control. Actually, it's quite okay. If you compare to the mean chart just now, mean chart is go up and then suddenly bounce back. But if you compare the same data, but you use a range chart, you see actually in the range, in the process from sample 1 to sample 10, the process actually in the good standing, means it's in a good process. Okay. And in this case, it's a random process, random occurrence. Okay. Occurrence. So this is our comparison between the two. Okay. So this is the one that you see in the mean chart. This is the one you see in the R chart. Okay. So the rest you read. So if you put side by side the two chart, you will see actually what happened to the overall process. Then when you discuss about the graph, there are four trend. We call it a run. Sequence of sample, we call it run. So sample 1 and sample 10, 1 run, 2 run, 3 run, and 4 run. Okay, so this one is just quite consistent. If you stay between the ULC, this one a little bit going up already, right? But it's above the center line, most of the data. This one is going up, okay? This one is going down, okay? So this is quite direct lah. Okay, so this is the earlier observation that we do. The next one is that we want to go deep a little bit on analysis when you do control. So as you can see, there's an equation come out on the right here. So if you see on the right here, the equation here is A and R hat. A is the mean chart actually, right? So you have a mean X bar, and this is double hat. It's a mean chart actually. So you divide your chart into 1 sigma, 2 sigma, 3 sigma. It's like the rotated sigma graph. Okay, so this is this is a center, and then the first zone, second zone, and third zone. The yellow color is 1 sigma zone, but 1 sigma again you have a upper and lower region, but you still consider as 1 sigma zone or zone C. Zone C. Then 2 sigma is zone B, 3 sigma is zone A. There's an equation over here. You just plug in and use the equation. Okay. So this is called pattern test when you do Six Sigma analysis. So pattern test is to determine if the observation within the limit of the control display a non-random pattern. So just now we are looking at random pattern. So what happened if you say the data is non-random? How you determine whether the data is random or non-random? You look at the data fall into zone A, zone B, or zone C by using pattern test. Okay. But again, your final exam is not required to use pattern test. Okay. We are going to discuss this now. Okay. You see the example. Okay. So this one you read. So okay, so you see pattern of sample observation on this zone then used to determine if any random pattern exists. So this one is fall within the control limit. But you want to test whether the sample is random or non-random. How you test? You are using pattern test. So the pattern test is actually all the equation that you see on the graph here. Okay. So what do you observe here? I give you all. So there are a few observations here. Is that in general guidelines, if you want to do pattern tests, there are some guidelines there. So when you use this guideline, none of the observation is obeyed beyond the control limits. So this is the general, this one. So the first one, 8 consecutive points are on the one side of the center line. So if your data is all the points is more than 8 points are on the left hand side or one side on the top or on the bottom, then this is we call it this one you should investigate You should investigate what happened to the data. So these are the guidelines for you to identify patterns. So if so the first one you look at whether is most of the data is on one side or not. Second one, consecutive point up or down, So this one is continuous up. Consecutive point up means is going up. The trend is going up or going down. 4 point alternating up or down. 4 point alternating means 1 point up, 1 point down, 1 point up. You count out 1, 2, 3, 4. Like if we go zigzag, then it's fall into this one. 2 out of 3 consecutive point in zone A. 2 out of 3 consecutive point means you look at three points. If they continuous fall into zone A, which is very near to your control limit already. Zone A is at the 2 side. Means something you need to control already. 4 out of 5 consecutive point in zone A or zone B. Zone A or zone B means you have a consecutive point. As long as you see consecutive point more than 3, then you need to control it. Okay. So if you look at the example, this graph violates rule number 1. It violates rules number 1. As you can see, more than 8 points are on one side of the center line. Rules number 4 also violated. You have 2 out of 3 consecutive points in zone A. 1, 2. This is 3 ma. 1, 2, 3. But rules number 4 is say 2 out of 3 consecutive points. 1, 2, 3. There are 2 points that is in zone A. So it violates rule number 4. It also violates point number 5. 4 out of 5 consecutive points are in zone A or B or one side of the center line. So zone A or B, you count 5 consecutive points. 1, 2, 3, 4, 5. Okay. So this is example. Okay, we won't go deep into this one. You go and do. So for the bearings example, what you do is that you build a new table. Which is you look at the average value. You copy this line, this column, mean. You copy outside, then you determine whether it's above or below the center line. Of course, this one a little bit hard to see. It's better you use graph to look this one. But this is just to help you to look at the pattern. So if you plot the same graph, okay, before that, how you know whether it's up or down, or which zone is this? You need to use the equation. The equation is on the graph here, so there's a plus minus 1/3 AR sigma. Why 1/3? Because you break the region into 3. From the center line to the below here, you have 3 zones, so you divide by 3. Okay. Why negative? Because it moved to the below, and this is below my lower control limit, so you have a negative. So this is towards positive. You have a positive because you are near to the upper limit, positive. Okay. So you calculate 1/3 is what first? 1/3 A2 again from the table. R hat you calculate already just now. So you calculate 1/3 is what value? So one of this range is 0.022. Okay, so you plot the graph lah. You plot the graph. You go back to the mean chart just now that you plot. You measure the thing. So 0.02. The mean is 5.01. You plus this number is about 5.03. Yeah. So this is your first zone, which is your build your zone C. You have positive and negative. So you take this number 5.01 minus 0.02. Okay, you get another half and so on. You add more and more. So 2, you add another 0.2. So this one plus 0.2, you get 0.05 and so on. Okay. Okay. So the 2R here is about 0.06. So it's about there. Okay. So you take this one 0.06, about 7, plus 0.01, you get about 5.08, about there. Okay. You do the rest for the negative side. So from the dot line there, you actually compare to the standard chart here. You have your zone A, zone B, zone C, zone 3 zone, zone A, B, C. So on the top, on the middle here is zone C, zone B, and zone A at the control limit line there. Then from there, you build this table, whether it's above or below. So for example, point A is here, point 1, 4.98. 4.98 is below the mean here. It's below, so it's B. Then the second line, 5 point something is here, also below the mean, so it's below, and so on. Then you check the general guidelines there. Does it consecutively doing the behavior? Okay. Okay. Then the process capability is depending on your standard variation or sigma's value that you set. So for example, the normal graph that we use in academic is that we use the natural variation. So you see there's a normal graph here, and you spread your specification in how many sigma that you want to control, right? The previous example you see is 3 sigma. So you stretch the range to the end of the graph there. Okay. So is this one. B, you stretch the design specification a little bit near to this one. So this one is if you have an upper limit, lower limit, you stretch to the end of this one. Let's say this graph you see is about 99%. So this one is process is capable of meeting specification most of the time. But if you pull the standard variation, the goalpost that you have, maybe 2 sigma here, 2 sigma here, the process is not capable of meeting specification all the time because you are actually narrowing the acceptable value. Here to here is acceptable value. But if you pull the goalpost nearer and nearer, means you have a very strict, not very strict lah, but you have a your QA system, your QA department will have a headache lah if you pull your sigma a bit closer and closer. This one, you see the two end of the normal graph here and the control limit. This one is always conforming to the specification. Means your data is always fall between the upper and lower. Okay. Then this one is a bit offside. It's a bit off already. The data got some data. Some output will not meet upper specification. So this is upper. Okay. So these are general ideas of what they have there. Okay. Okay, we go a little bit more. Then we have a short break. After a short break, we'll do revision already. Do revision. Okay. So this is the scope that you already in our chapter 8, also in your module. Some of it we already cover in the previous lecture. So this about 5 minutes time. We'll just flip through the review. What are the ideas that you should understand? Okay. So we also cover what is quality previously. Design for Six Sigma. We already cover what is Six Sigma previously. Right. Six Sigma is a system we use to check our quality. Right? So our quality tools. So this is a range of the data. So in this case, if your upper and lower limit means most of the time your data is conforming to the specification, because this is your out range, your limit. If all your data is between these two orange color line, means every time your process is meeting the specification. Okay. Design to Six Sigma is designing a product that meeting the specification of what your customer wants. Okay. Design to cost means you need to consider overall cost. most of the time, if your process is designed to the cost, you are reducing the cost in the production process. Okay. So these are the tools that you'll be using. Concurrent engineering we already cover in the chapter 7. Quality function deployment, this is, I'll give you information later. Rhombus design, statistic control process, we already cover for the P chart, C chart, and also the mean chart, range chart just now. Okay. So these are the benefit on where we use them, right? So concurrent engineering is when you have a design process and planning. You go parallel to save time and also cost also. QDF, quality function deployment, this one is to highlight the customer requirement in the process. Rhombus, RD, focus on designing quality, eliminating loss. This one is eliminating loss. Loss means waste. You want to reduce waste. Statistical control process, you look at the process, whether in control or out of control. Poor quality is also same like the rhombus design and so on. Concurrent, you already learned previously, right? So again, Six Sigma, you're seeing the range again. Kaizen is important when you go to works later, especially in the those manufacturing plant, especially those Japanese company. It's a very, very old concept, but they already like built inside the company already. They assume you know what is Kaizen. Okay, so Kaizen is a continuous improvement. So if you in the Japanese company and they practice Kaizen culture, you have to give solution all the time. You will see a lot of checklists. Then in the checklist, every time you need to mention corrective action is what? What is a corrective action, right? Okay, the rest you read. Okay, again, IPPDD, Integrated Product Development and Design. So it's very old ideas. It's the first introduced by United States Defense of Department, DoD, Department of Defense, when they developed their weapon and also for space program, and they will use IPDD. So this is a chart, okay. So these are the concurrent engineering steps. There are a few steps you read through. Okay. Number design, also you read through. I'm supposed to ask you this one in your final exam, but for your short semester, I don't ask you this one. But your junior batch will see all these questions. Right. Again, I need to highlight what is Taguchi approach. Taguchi is a famous approach, especially again, you are dealing with Japanese company. They like to use Taguchi approach, where they use statistics to analyze whether the process good or not good. Taguchi, the main word here is for optimization. You want to optimize the quality. Okay. We won't go deep into how to do Taguchi, but general idea, Taguchi is for optimization. Right. You know what is optimization, right? For example, for structures, you use honeycomb structure and so on. Okay. Okay. Loss function. This is also you have left limit, upper limit, but your y-axis is loss. So you want to find the optimal value at the center. You don't want to go to the left or don't want to go to the right. That is the ideas lah. Okay, and loss function is important for quality, especially production manager. They will need to report the Taguchi approach analysis results, whether this process is anything happen to the product or not. Okay. 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 Rhombus design, we read. Okay, so this one already very expert already. We already cover this one very extensively. What is the X bar chart? What is all this chart? Okay. So 4 step in a statistical process, you measure, then you do analysis, then you monitor, then you improve. These are the steps to do. Okay. So okay, the rest is you read lah. This all the add-on information. This one go very deep into Six Sigma already. Okay, but I don't think I need to cover this one. But you go and read lah. So section 3.8.7, you go and read. Okay, I flip through lah. What is inside? How to do the coding? Like what is your input? What is output? And so on. Okay. So Six Sigma already cover. Okay, so these are the history of quality management. Okay, go and read lah. Okay, one is lean production. In the example, how you do lean. Okay, this one also you read. So there are calculation for lean, Six Sigma, what is half wheat and so on. But this one, I don't test you. Okay, so this one have a quiz lah. So let's just go through. Okay, 5S I also need to highlight because when you go to work, 5S also in the quality system. What is 5S? 5S is all this lah. Especially those Japanese company again, right? Sort, set in order, shine. Shine means clean, clean your desk, clean your environment. Standardize means there is a checklist. Everything you do, there is a checklist. Sustain means continue to do. If nothing, if the quality is acceptable, continue to do. Okay, 5S. 5S objective is to improve efficiency and eliminate waste. All this. So the rest you read. Okay, another one is Pokayoki. Pokayoki is go, no go design. It's important if you join the design department. Pokayoki, they assume you know already from the first stage you join the department. So even in the interview, if you interview for R&D engineers, the chief engineer will sure ask you, do you understand what is Pokayoki? Can you give an example of a Pokayoki? If you like that, then you cannot get a job already. Pokayoki is go, no go. It's a go, no go design. For example, your SIM card. There's a certain way you insert SIM card. You insert you wrong way, it cannot go in one. Okay, or you cannot get this one. This is called Pokayoki. Means it's Pokayoki is they call it yes, idiot proof. Call it idiot proof. There are lots of design nowadays is a Pokayoki design. Okay. Your socket also. Socket 3-pin, 2-pin. They're also very idiot proof one. You can either go one way or cannot go in. Okay, you USB. But nowadays they use C port, right? C port also idiot because they don't care how you plug. You're still able to plug in. You're still able to charge. They also we call it a new. Previously, if you use Pokayoki, the C port actually they don't think they actually think outside the box already. Previously, you have a specific shape to fit inside the definition of Pokayoki. Okay. This you read, okay. Lane, this is a quiz question. What is lane? Pokayoki. Design experiment also you read. Okay. This is a t-test. How many tests you do? Quality management. Okay, TQM also total quality management. It's all the component here. Okay. A conduct company, of course, they go bankrupt some way in the history. But they do have a very useful QA system, a quality system. They focus on customer, analytic process, and teamwork, and then continuous improvement. This quality improvement principle is very famous in the this total quality community. And ISO, if you see the company, before you go to interview, you look at the company profile, they show ISO 9001. It means they are very particular in their quality. You sure see the Takochi system, you'll still see the Six Sigma and so on. Okay. Okay. The rest you read. It's already covered already in previous this one. Many courses lah, so you can read. So I read how to use all histogram, all this you read. Pareto graph, trend analysis, control chart, already cover. Six Sigma, Lean Six Sigma, Pokayoki, your seat belt, plug, and so on. Even your heart also Pokayoki. You only have one way of blood flow. Okay. Nowadays, if you work in the automotive, you have all these sensors. They also Okayoki system. It's a prevention. It's a prevention. Everything automatic prevention. Okay. Okay. With this, we conclude chapter 8. Okay, we continue 910, 10 minutes breaks. Okay. Sign your attendance.